तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last two lectures, we saw about permutations and combinations. PNR denotes the number of permutations of R objects out of N objects, and CNR denotes the number of combinations of R objects out of N objects. And we have seen some results about this where repetitions are allowed and where different types of arrangements are considered and so on. We also saw that how to distribute distinct and non-distinct objects into distinct cells, and what is the connection between them and permutations and combinations. And today we shall look at the same thing, combinations and permutations, but from a different point of view, making use of a tool called generating functions. Here also we will see about combinations and permutations, but we are going to get the answers or the formula using some other method, the concept of a generating function. So, what is a generating? Generating function, we shall see two types of generating functions, the ordinary enumerator and also the exponential enumerator. Now, from three distinct objects A, B and C, there are three ways to choose one object, namely to choose either A or B or C. Let us represent these possible choices symbolically as A plus B plus C. So, if you have three objects A, B, C and you want to select one of them, you can choose A or you can choose B or you can choose C. That you can represent as A, B, C, A plus B plus, A or B or C. Similarly, from these three objects, there are three ways to choose two objects, namely you can choose either A and B or B and C or C and A, and this can be represented symbolically as AB, A and B, B and C, C and A and B or B and C or C and A. And if you want to choose all the three objects, then there is only way of doing it, and that can be symbolically represented as ABC. Now, if you look at this polynomial 1 into 1 plus Ax into 1 plus Bx into 1 plus Cx, this formula, if you expand this, this is equal to 1 plus A plus B plus Cx, AB plus BC plus CA x squared, AB C x cubed and so on. Now, the coefficient of x power 1, x is x power 1, represents the number of or the possible ways of choosing one object. The coefficient of x squared is AB plus BC plus CA, and that represents the possible ways of choosing two objects out of the three objects, that is AB, BC or CA. The coefficient of x cubed represents the possible way of choosing all the three objects ABC, that is ABC. Now, we discover that all these possible ways of selection are exhibited as the coefficients of the powers of x. Now, how do you interpret this? The factor 1 plus Ax, it means that for the object A, there are two ways of selection. One is not to select A, that is one way of doing it, and another one is to select A. So, that is represented as one means not selecting A, the other is selecting A, Ax. So, it is represented like this. Now, if you look at the left hand side of that equation, previous equation, this portion, this is the product like this. This means that for the object A, B and C, the ways of selection are to select or not to select A, that is represented by this factor. And you can select or not select B, and that is represented by this factor. You can select or not select C, and that is represented like this, right. So, together this gives you the number of ways of selecting one object or two objects or three objects out of the three objects A, B, C, and that the coefficient of x power r on the right hand side gives you the possible ways of selecting r objects out of these three objects. In general, you can see that if you have a sequence A0, A1, A2, AR be the symbolic representation of a sequence of events, or let it be simply a sequence of numbers, then the function fx is equal to A0 mu naught x, A1 mu 1 x, A2 mu 2 x, etc., AR mu r x is called the ordinary generating function of the sequence A0, A1, A2, AR, where mu naught x, mu 1 x, mu 2 x, mu r x is a sequence of functions of x that are used as indicators. This is the sequence A0, A1, A2, AR, this is the sequence, and you are using the indicator functions. This mu naught x, mu 1 x, mu 2 x are called indicator functions. Using these sequence of functions as indicator functions, if you represent fx like this, that is called the ordinary generating function of the sequence A0 mu naught x, A1 mu 1 x, and so on. If you look back, you see here the sequence is 1 A plus B plus C, AB, BC, CA, AB plus BC plus CA, and ABC. And if you use 1 x, x squared, x cubed, etc. as ordinary as indicator functions, this is the ordinary generating function. If you, for example, if you use as indicator functions 1 cos x, cos 2x, etc. as the indicator functions, then the ordinary generating function of the sequence 1 omega, omega squared, omega cubed, etc. is given by this expression f of x is equal to 1, plus of course here the function is 1, then omega, second here you have cos x, then you have omega squared, third here is cos 2x, so you have cos 2x here, and so on. So, for omega r you will have cos r of x. So, the expression is 1 plus omega cos x, omega squared cos 2x, etc., omega power r cos r x. This is the ordinary generating function for the sequence 1 omega, omega squared, etc., using the sequence 1 cos x, cos 2x, cos r x as indicator functions. Now, the indicators functions you can choose in any way, but you have to choose them in a proper manner that a particular sequence can be represented in a unique manner, or one expression uniquely represents one particular sequence. Two sequences should not give rise to the same expression or the function. Let us see, using 1 plus x, 1 minus x, 1 plus x squared, 1 minus x squared, etc. as indicator functions, suppose 1 plus x power r, 1 minus x power r as the indicator functions, and suppose you take this sequence 3, 2, 6, 0, 0 as a sequence, what will be the ordinary generating function? 3 into 1, 2 into 1 plus x, 6 into 1 minus x, 0 into 1 plus x squared, 0 into 1 minus x squared. That is 3 plus 2 into 1 plus x plus 6 into 1 minus x. If you simplify, this will reduce to 3 plus 2 plus 6, 11, 2x minus 6x will give you minus 4x. So, the ordinary generating function becomes equal to 11 minus 4x for this particular sequence using these as indicator functions. Now, this expression, it should not represent another sequence for the same set of indicator functions. In that case, it is not advisable to use them as indicator functions. Look at this sequence 13700 and 12611 with the same set of indicator functions. What will you get? What will you get as the generating function? 1 into 1, then 3 into 1 plus x, 7 into 1 minus x, 0 into 1 plus x squared, 0 into 1 minus x squared, and so on. Let us see what you will get here. 1 plus 3 into 1 plus x plus 7 into 1 minus x. This will reduce to 1 plus 3 plus 7, 11. 3x minus 7x will give you minus 4x. So, same 11 minus 4x you are getting, and it is representing this particular sequence as well as this sequence. It also represents another sequence. See, suppose you take the sequence as 1, 2, 6, 1, 1. Let us see what is the ordinary generating function for the same set of indicator functions. We have 1 into 1, 2 into 1 plus x, 6 into 1 minus x, 1 into 1 plus x squared, 1 into 1 minus x squared. If you simplify this, you realize that you get 1 plus 2 plus 6 plus 1 will give you 11. This x squared will cancel with this x squared, and as far as the coefficient of x is concerned, you have 2x minus 6x, which will give you minus 4x. So, again you see that you are getting the same ordinary generating function, and it is representing 3 sequences, which is not correct. So, these functions you cannot use as indicator functions. The indicator functions should be such that for each sequence the expression you get is unique, or each expression uniquely represents a sequence. Now, the easy way out is you choose 1 x, x squared, x cubed, x power 4, x power r, etc. That is, this sequence is taken as the set of indicator functions. In that case, the coefficient of x power r gives you the value ar, the rth element in the sequence which you want to represent, and there is only one way of doing it. So, there is no problem. So, usually 1x, x squared, x cubed, etc. They are taken as indicator functions. So, we shall restrict our consideration to only those sequences. Now, let us see how the generating function can represent a combination. We have earlier seen 1 plus ax into 1 plus bx into 1 plus ax, how it represents the way of choosing a, not choosing a, choosing b, not choosing b, choosing c, not choosing c, etc. Now, put a is equal to b is equal to 1 in that expression, then you will get 1 plus x into 1 plus x into 1 plus x, that is 1 plus x cubed, equal to 1 plus 3x plus 3x squared plus x cubed. What is this 3? This, the coefficient represents the number of ways of not choosing any objects out of 3 objects. This gives you the number of ways of choosing one object out of 3 objects. This gives you the number of ways of choosing 2 objects out of 3 objects, and the coefficient of this gives you the way of choosing all the 3 objects. So, the coefficient of x power r gives you the number of ways of choosing r objects out of n objects. In general, if you generalize this, to find the number of combinations of a distinct object, we have the ordinary enumerator, ordinary generating functions. This is a binomial function, binomial expression. 1 plus x power n is 1 plus nx plus n into n minus 1 by 2 factorial x squared, etc. Or you can represent this as c n naught c n1 x plus c n2 x squared and so on. The coefficient of x power 0 or the constant term here is the number of ways of choosing no objects out of n objects. The coefficient of x power 1 or x is given by this. This is the number of ways of choosing one object out of n object. The coefficient of x squared gives you the number of ways of choosing two objects out of n objects, and the coefficient of x power r gives you the number of ways of choosing r objects out of n objects. Of course, the last term, the number of ways of choosing all the n objects out of n objects is 1, cnn is 1, that we know. In the expansion of 1 plus x power n, the coefficient of the term x power r is the number of ways of the term x power r can be found by taking r x's and n minus r ones among the n factors 1 plus x. So, that is you are selecting r object and leaving out n minus r objects out of n objects. So, using this generating function concept, you can prove certain identities. For example, you have this. This is the expression we have earlier seen. Instead of writing CNR, we are writing it as NR. This also represents the number of ways of choosing R objects out of N objects. So, CNR can also be written in this form. That is what we are making use of here for simplicity. Now, from n, this is the binomial expansion, cn0 cn1x plus cn2 x squared, etc. is equal to 1 plus x power n. Now, in this equation, you put x is equal to 1. If you put x is equal to 1 here, this becomes 2 power n. And here, if you put x in every place, you get this. The left hand side becomes this. What is this? This is the number of ways of choosing 0 objects or 1 objects or 2 objects or 3 objects or n objects out of n objects. This is the number of ways of choosing 0 objects. This is the number of ways of choosing 1 object, number of ways of choosing 2 objects, and so on. You can very easily see that from a combinatorial point of view, you have n objects. For each object, you have two possibilities. Either you can select or not select. So, if you for n objects, there will be 2 power n possibilities. Each object you have 2 possibilities. For n objects, the possibilities will be 2 power n. That is what you get on the right hand side. So, the number of ways of choosing 0 objects, 1 object, 2 objects or n objects out of n objects, that is the left hand side, is seen to be equal to 2 power n. So, from combinatorial point of view also we are able to see this, and we can get this from the binomial expression also using the idea of generating function. So, this is what we have seen. By setting x is equal to 1, we got that. Setting x is equal to minus 1 in the previous one, this will become 0 and alternate terms will become negative. This will be negative, this will be positive, this will be negative, and so on. So, you will get n0 minus n1 plus n2 minus 1 power r nr minus 1 power n nn is equal to 0. Right hand side will become 0. So, if you take all the negative terms to the right hand side, this will be n0, n2, n4 and n1, n3, n5, cn0, cn2, cn4, etc. What does the left hand side represent? The left hand side represents the number of ways of selecting 0 objects out of n objects, or 2 objects out of n objects, or 4 objects out of n objects, and so on. What does the right hand side represent? It represents the number of ways of selecting 1 object out of n objects, 3 objects out of n objects, 5 objects out of n objects. So, the left hand side represents the number of ways of selecting an even number of objects from n objects. The right hand side represents the number of ways of selecting an odd number of objects from n objects. We see that the number of ways of selecting an even number of objects is equal to the number of ways of selecting an odd number of objects from n distinct objects. The left hand side is equal to the right hand side. So, the number of ways of selecting an even number of objects from n objects is equal to the number of ways of selecting an odd number of objects from n objects. This also you are able to get from the generating function idea. Now, look at this. This is an identity. How can you prove this identity? Cn0 squared, n1 squared, n2 squared, etc., Cn2 squared, Cnr squared, etc. is equal to C2nn. This can be proved in 2 ways. Let us see how we can prove this. Look at the ordinary enumerator, 1 plus x power n, that is n0 plus n1x plus n2 x squared plus nn x power n. Look at 1 plus 1 by x power n, that is equal to n0 plus n1 into 1 by x plus etc. plus nn to x power n. I am sorry, this is 1 by x power n, 1 by x power n. Now, if you multiply these two, you consider 1 plus x power n into 1 plus 1 by x power n. That will be, you have to multiply this whole thing by this. Now, what is the coefficient of x power 0 or the constant term here? Right hand side will be some expression. Okay. What is the coefficient of x power 0 or the constant term? Coefficient of constant term. This and this will give you a constant term, that is n0 the whole squared, and this when you multiply with this will give you a constant term, that is n1 the whole squared. This and the coefficient of 1 by x squared will give you a constant term. So, that is n2 squared and so on. And lastly, when you multiply this by this, you get a constant term, and that is n. Thus, you get the left hand side of the expression which we want to prove. So, we want to prove this, that is, this is equal to this. So, by considering this and multiplying out, you get the coefficient of x power 0 or the constant term as this, which is the left hand side. Now, how do you get the right hand side? You have 1 plus x power n, this is what you are considering, right? 1 plus x to the power of n. Now, this one you can write as 1 plus x power n, this x if you take, it is x plus 1 power n by x power n, or x power minus n, this is 1 plus x power 2n. In this expression, if you take the coefficient of x power n, when you multiply it by x power minus n, you get a constant term. So, what is the coefficient of x power n in 1 plus x power 2n, that is 2n, right? The coefficient of x power n in this is 2n power n. When you multiply this by x power minus n, you get the constant term. So, if you look at it in a different way, the constant term, constant term here is 2n, instead of saying coefficient of the constant term, I could have said constant term itself. The constant term is this, and the constant term, so it becomes equal to 2n n. So, you find that you look at it in two different ways, the expression 1 plus x to the power of n into 1 plus 1 by x to the power of n. Then in one way you get the left hand side, in another way you get the right hand side, they are equal. This is one way of looking at it. You can also prove it by combinatorial argument. Now, the left hand side is n0 whole squared, but you know that NCR is equal to NC n minus r. This we know, the number of ways of choosing r objects out of n objects is the number of ways of leaving out n minus r objects out of n objects. So, this identity we know. So, making use of that, the left hand side will be equal to n0 and nn plus n1 n minus 1 and so on plus nn n0. By a combinatorial argument, what does this represent? You have 2n objects and you separate them into two sets of n objects. Now, I want to choose n objects out of 2n objects. I can choose 0 from here and n from here, which is given by this expression, or I can choose 1 from this set and n minus 1 from this set, and that is given by this. I can choose 2 from this set and n minus 2 from this, that will be this the next term. And the last I can choose all the n from this and 0 from the second set. So, that is given by this. So, in essence, it amounts to the number of ways of choosing n objects out of 2n objects, and we know that that is given by 2n n. So, by a combinatorial argument also you can prove this equality. Now, let us consider a small problem. What is the coefficient of the term x power 23 in 1 plus x power 5 plus x power 9 to the power of 100? You have 1 plus x power 5 plus x power 9 to the power of 100. You want to find the coefficient of x power 23. How can you find this out? Now, how can you get 23 by having 5s, 9s and 1s? There is only one way of doing it. You can have 5 plus 9 plus 9. This will give you 23. Otherwise, if you have 4 5s, then you will have 3, which is not possible. If you have 2 5s, then also you will be left with 19, which you cannot account for. 3 5s, then you will be left with 8, which is not accountable. So, there is only one way of splitting 23 into 5s and 9s, and that can be done only in one way. So, if you have 100 factors like this, out of the 100 factors, you have to select 2 factors or x power 9 from 2 factors and x power 5 from 1 factor, then only you will get x power 23. So, you have to select x power 9 from 2 factors out of 100, and you have to select x power 5 from 1 factor, that is out of 100, out of the remaining 98. So, it will be C 102. From 2 factors you are selecting x power 9. After doing that, you will be left out with 98 factors from which you have to select 1 x power 5. That can be done in C 98, 1 From the rest of the factors you have to select only one. So, this will give you the answer 100 into 99 by 2 into 98. You can simplify, multiply and get the answer for the expression. This is the number of ways of, this is the coefficient of x power 23 in this expression. When you allow repetitions, what happens? You are having 3 objects A, B, C, but you allow repetition now. For A, you can choose it 2 times, either once or twice you can choose, and B and C you can choose only once. In that case, how does the expression become, or how does the generating function look like? When repetitions are allowed in the selections, or equivalently when there is more than one object of the same kind, or you can look at it like this, you are having 2 red balls, 1 blue ball, 1 green ball, and then from which you have to select 1, 2, 3 balls and so on. The extension is immediate. You can look at it like this, 1 plus Ax plus A squared x squared. That is, the object A can be need not be selected, or it can be selected once, or it can be selected twice. The object B can be not selected or selected once. The object C can be not selected or selected once. Now, if you expand this, you get this, which means if you want to select one object out of the 3 objects where A can be selected twice. See, when you select only once, it does not matter whether you can select twice, or the coefficient becomes only A plus B. The coefficient of x tells you the number of ways of selecting one object out of 3 objects A, B, C, where you allow A to be selected twice. But when you look at the coefficient of x squared, the possibilities are like this. Either you can choose A and B, or you can choose B and C, or you can choose A and C, or you can select A twice. So, A squared also is in this term. Similarly, when you want to select 3 objects out selected twice, you can select A, B, C, or you can choose A squared twice and B once, or A squared twice and C once. And if you want to select 4 of them, A has to be selected twice, B and C also have to be selected. So, this is the ordinary generating function for the combinations of the objects A, B, C, where A can be selected twice, or you are allowing A to be selected twice. You must note the difference between this and the polynomial 1 plus Ax into 1 plus A. See, we have considered like this, 1 plus Ax plus A squared x squared for the selection of A. It is not the same as 1 plus Ax into 1 plus A squared Cx, because in this case the expression will become like this. This is different. Here you are allowing A to be selected once, twice, thrice and so on. So, that is not the same thing. So, if you look at this expression 1 plus Ax into 1 plus A squared x to 1 plus Bx into 1 plus Cx, etc. If you expand, it will be like this. What does this represent? It represents the following thing. You can imagine that there are 4 boxes, one containing A, one containing 2 A's, one containing B and one containing C. The generating function gives the outcomes of the selection of these boxes. So, you are having 4 boxes. This box contains 1A, this box contains 2A's, this box contains B, this box contains. If you select one of them, what will be the outcome? It could be A, or it could be B, it could be C, or it could be A squared. If you select two boxes, then if you choose the box containing A and B, you will get AB. If you choose the box containing B and C, you will get this. If you choose the box containing A and C, you will get this. But if you choose the box containing A squared, one another box you can choose. So, A squared and A will give you A cubed, A squared and B will give you A squared B, A squared and C will give you this. Similarly, for the coefficient of x cubed and x power 4. So, this represents that there are 4 boxes, one containing A, one containing 2 A's, one containing B and one containing C, and this generating functions gives the outcomes of the selection of the boxes. When you select one box, what happens? When you select 2 boxes, what are the things inside that, and so on. This is different from what we considered earlier, this one, where you have 3 objects A, B, C, where one object is allowed to be selected more than once. That is, A is allowed to be selected twice. Now, instead of putting A, B, C, if you put them as 1, so the ordinary enumerator for the combination of the objects A, B, C, where A can be selected twice, is given by this. Instead of A and all, you have just considering the number of A's only. So, it is 1 plus x squared into 1 plus x into 1 plus x. For B it is 1 plus x, for C it is 1 plus x, for A it is 1 plus x squared. If you expand this, you will get this. So, the number of ways of choosing one object out of 3 objects A, B, C, where A you can select twice, is 3. So, if you have 3 objects A, B, C, the number of ways of selecting one of them is you can choose A, you can choose B. Them is you can choose A, B, that is 1, you can choose B, C, that is 1, you can choose C, A, that is 1. A can be selected twice. If it is selected twice, that gives you 1. So, totally it is 4, and that 4 represents that. The coefficient of x squared represent like this. Like this you get the coefficient of x cubed and x power 4 also. The significance of the factor 1 plus x squared is that the object A, there is one way not to select it, one way to select it once, and there is one way to select it twice. That is what is meant by this expression 1 plus x squared. Given 2 each of p kinds of objects and 1 each of q additional kinds of object, in how many ways can R objects be selected? This is the problem. Let us see how we tackle that. So, you have p objects, they can be selected twice, given 2 each of p kinds of objects. So, if you take one of them, you can select it once or you can select it twice. Okay. This is the enumerator for the p kinds of objects, and you are having q additional kinds of objects, each you have only one of them. So, either you can choose them or not choose them. So, this is the enumerator for the expression, and generally see first object you are having 2 of them, second object you are having 2 of them, like that p of them, then q of them you are having only 1. Okay. So, the first object you can select once, you need not select, or you can select only one of them, or you can select 2 of them, like that for all the p objects. So, the enumerator for that is this ordinary enumerator. Then the remaining q objects you are having only one of them. So, either you can select it or not select it or not select it, and totally you are expected to select R objects out of the p plus q, out of the actually 2p plus q objects. In that case, what is the number? This is, you have to find the answer is the coefficient of x power r in this expression. Now, what is the coefficient of x power r in this? Now, you can select x squared I times, then that will give you a power of 2i. Then there will be how many factors remaining here? There will be p minus I factors remaining here, and already there are q factors. Out of these factors and these factors, you have to select the remaining coefficient x power r. This is the remaining coefficient you have to choose. So, the idea is, if you say it is sigma I is equal to 1 to r by 2 from these p factors you have to select. So, p I, and from the remaining p minus I plus q factors, that is p plus q minus I factors, you have to select and this r, if it is even, this is okay, otherwise you have to select the integral part of that. This will give you the answer. What does that mean? It means that suppose r is 13, 13 means you cannot select x squared, 13 by 2 is 6.5, you cannot select 6.5 times this. So, you have to select 6 times x squared, maximum you can select is 6 times, and 1 you have to choose from here. So, from I is equal to I times your I factors you are selecting here, and that will account for 2 power I. The rest of them you have to select from the p plus q minus I factors. So, this will give you the answer for this problem. Now, the ordinary enumerator for the selection of r objects out of n objects, where r is greater than or equal to n with unlimited repetitions, but with each object included in each selection is this. Now, before that each object is need not be included. So, you are selecting r objects out of n objects. What is the expression for this? This we know is C n plus r minus 1 by So, we are selecting r objects out of n repetition, and the expression for that is C n plus r minus 1 r C n plus r minus, both are equal. How do you get this? See, you get 1 plus x squared etc. For one object it can be selected, it need not be selected at all, or once, or for one object the enumerator is this. For n objects the enumerator is this, and this is nothing but 1 by 1 minus x whole power n, or equal to 1 minus x to the power of minus n. In the binomial expansion, this will expand as 1 plus nx plus n into n plus 1 by 2 factorial x squared and so on. the coefficient of x power r will be n into n plus 1 etc. n plus r minus 1 by r factorial x power r plus etc. If you expand using binomial theorem, this will be the expression. Now, the coefficient of x power r will give you the number of ways of selecting r objects out of n objects with unlimited expression, and this is this expression, and this is nothing but this. Okay. This we have earlier seen by different arguments. Now, if you have to select each one of the n object at least once, then what is the expression? We will consider that. The ordinary enumerator for the selection of r objects out of n objects, now r has to be greater than r equal to n, because each one of them you are selecting at least once with unlimited repetitions, but with each object is included in each selection, that is given by this expression x plus x squared plus x power 4 etc. to the power of n. For each object, the possibility is it can be selected once, twice, etc. Please note that the possibility, the constant term plus 1 which was there in the earlier case is not here, because you have to select each object at least once. So, the ordinary enumerator is given by this expression, and if you take out the x power n, this is equal to x power n into 1 by 1 minus x power n to the power of minus n. And this expression, if you simplify this, if you expand this portion and simplify, x power n is like this. The expression for 1 minus x power minus n using binomial expression is sigma I is equal to 0 to infinity n plus I minus 1 I, that is c n plus I minus 1 I x power I. This is the way you expand this 1 minus x to the power of minus n. So, this will be sigma I is equal to 0 to infinity n plus I minus 1 1 c, that is a combination c n plus I minus 1 I x power n plus I. Now, put n x plus I with unlimited repetition, where each object is selected at least once. So, if you put n plus I is equal to r, this the previous equation becomes, here it becomes r, but I will be now from, so instead of saying I is equal to 0 to infinity, you can say r is equal to 0 to, r is equal to n to infinity. So, this is x power r, then instead of saying I is equal to 0 to infinity, now it will be r is equal to n to infinity. So, the expression for that is r minus 1 r n, r minus n, n plus I is r, so it will be r minus 1 I, r is equal to n plus I, so I will be r minus n. So, this is rewriting that previous expression, it will be equal to c r minus 1 r minus n x power r, where the summation ranges from r is equal to infinity. Now, the coefficient of x power r, which is r minus 1 r minus n, you can also rewrite this in this way, because c n r is equal to c n n minus r. You can rewrite this expression like this. The coefficient gives you the number of ways of selecting r objects out of n objects, where each object is selected at least once. We have seen this expression also in the case of distributing r objects into n distinct cells, where each cell should contain at least one object and so on. As an application, let us see a simple problem. what is the number of ways in which 4 persons each rolling a single die once can have a total of 17. We are having 4 people, each person is rolling a die, and the outcome of each die will be between 1 and 6, and what are the number of ways we can have a total of 17 from that. So, for one person it could be 1 or 2 or 3 or 4 or 5 or 6. So, the outcome can be like this. So, you are having 4 persons. So, ordinary enumerator for that will be x plus x squared plus x cubed plus x power 4 plus x power 6 to the power of 4. And you have to find the coefficient of x power 17 in this. So, we have to find the coefficient of x power 17 in x plus x squared plus x power 6 power 4. So, this we can write as x power 4 into 1 plus x squared plus x power 5 to the power of 4, and this is a geometric series. So, this you can write as x 1 to the power of 4. So, in essence you have to find the coefficient of x power 13, because 4 you are accounting for here, in 1 minus 6 to the power of 4 to 1 minus x to the power of minus 4. Let us see what is that coefficient. 1 minus x power 6 to the power of 4 is 1 minus 4 x power 6 plus 6 x power 12 minus etc. And 1 minus x power minus 4 is 1 plus 4x plus 4 into 5 by 2 factorial x squared plus 4 into 5 into 6 by 3 factorial x cubed etc. So, in the product we have to find the coefficient of x power 13. How can you get x power 13? You can multiply this by x power 13 here, the term consisting of x power 13 here, and you can multiply this by the term having x power 7 here, and you can multiply this term by this term. So, in 3 ways you can get x power 13. So, let us add those coefficients. So, if you multiply this 1 by the coefficient of x power 13 here, what will be the coefficient of x power 13 in this expansion? That will be 4 into 5 into 6 up to 16 by 13 factorial, because we are considering the coefficient of x power 13, then minus the product of this term with the coefficient of x power 7 here. X power 6 and x power 7 will give you x power 13. So, that is 4 times 4 into 5 into 6 up to 10 by 7 factorial. Then if you multiply x power 12 by x, you get x power 13. So, these two will give rise to another x power 13, that is 4 into 6. So, if you simplify this, you can multiply by and divide by 1 into 2 into 3, 4 into up to 16 by 13 factorial minus 4 times 1 into 2 into 3 by 1 into 2 into 3 up to 10 by 7 factorial plus 24, and this will be 14 into 15 into 16 by 6, 13 factorial will cancel off. Here again up to 7 you can cancel off. So, this will give rise to 4 into 8 into 9 into 10 by 6 plus 24, and this is 7, 3, 5, 35 into 16, 35 into 16 minus this is 448 into 10 plus 24, and this will be, you can write it here, 16 into 5, 80, 48, 560 minus 480 plus 24, this 80 plus 24, 104. So, there are 104 ways in which you can get 17 by rolling 4 dice. So, we have considered some examples here, and we have seen how the concept of a generating function, an ordinary enumerator, can be used to solve some problems in combinations, the number of ways of selecting. But when we consider the number of ways of permutations or arrangement, there is a slight problem. The very big advantage in using an ordinary enumerator is that the binomial coefficients CNR, they give you the number of ways of selecting R objects out of N objects. So, you have a very simple closed form expression, whereas the same will not be true in the case of permutations. So, in the case of permutations, what sort of an enumerator we should have, so that we get a decent closed form expression. So, in the next lecture, we will consider generating functions for expressing the permutations, number of ways you can permute R objects out of N objects.